Have you ever wondered how it's even possible to predict an entire election with just a few thousand phone calls? Or how a company can claim to know what millions of people think about their new product? Well, the secret isn't magic. It's a powerful idea called statistical sampling. And today, we're going to pull back the curtain and see exactly how it works.
So, here's our roadmap. We'll start with the big idea of making smart guesses. Then, we'll get to know our key players, the population and the sample. We'll look at why we even bother with samples in the first place, face the reality of something called sampling error, and then wrap up with the clever ways researchers fight back to make their guesses as smart as possible. All right, let's dive right in. How on earth can we learn about millions of people by only talking to a tiny fraction of them? I mean, think about it. You see it all the time with national elections or finding out the country's favorite TV show. Actually asking every single person, it's just not possible. It's way too big of a job. So what's the trick?
Well, the trick is that you don't have to ask everyone. You just have to ask the right someones. It all comes down to the science of making a really, really smart guess based on the data you get from a much smaller but very carefully chosen group.
And this whole process, it has a name: statistical inference. And honestly, it's an incredible idea. It's the concept that you can understand a massive whole just by looking closely at one small, representative piece. This is the engine that drives so much of what we know, from medicine to marketing. Okay, so to really nail this down, we need to get crystal clear on two words you're going to hear a lot: population and sample. And the best way to do that is to think about a giant pot of soup.
So the population, that's the entire pot of soup. It's everything we're interested in studying. It could be all the undergraduate students in the Netherlands, every single star in our galaxy, or all the cars on the road. The whole shebang.
Now, you wouldn't eat the entire pot of soup just to see if it needs more salt, right? Of course not. You'd take one spoonful. That spoonful, that's your sample. It's the small, manageable group you actually collect your data from to figure out what the whole pot is like. And let's add two more quick terms here. A parameter is a number that describes the whole population, the true saltiness of the entire pot of soup. It's the real value we're chasing. A statistic, on the other hand, is a number that just describes our sample, the saltiness of our single spoonful. The whole game is using that statistic from our spoonful to make a really good guess about the perimeter of the whole pot.
At this point, you might be thinking, okay, this seems obvious, but why not just study everyone if you want to be sure? It's a totally fair question. If we want to know about the whole population, why do we mess around with samples at all?
Well, it pretty much boils down to reality. For one, sometimes it's literally impossible to study everyone. But even when it's possible, it's just not practical. It saves a ton of time, a ton of money, and analyzing a smaller, cleaner dataset is just so much more manageable. Okay, but it can't be that easy, right? There has to be a catch. And there is. Here's the twist. That spoonful of soup is a really good approximation, but it is never going to be a perfect tiny version of the whole pot. And that little difference, that's crucial. What this really means is that there's always going to be a small gap between what our sample tells us and what's actually true for the entire group. It's not a flaw in the plan. It's just an unavoidable part of the process. This natural gap has a name: sampling error. And please, remember this. This is not an error, like somebody made a mistake. It's not a blunder. It's just the natural, expected difference you get when you look at a part instead of the whole. Your spoonful might have one extra carrot cube by pure chance, but it still tells you the soup has carrots. Now, while that random error is just part of the deal, there are other kinds of errors, actual mistakes that can creep in if you're not careful. Things like surveying the wrong group of people to begin with, or only getting answers from people who are super passionate about the topic. Those are the real pitfalls researchers work hard to avoid. So, if we know some error is just baked into the system, what do researchers do? Just give up? No way. They have some really powerful strategies to shrink that error down as much as possible, and even measure it so they can tell you how confident they are in the results. There are two main ways to tackle this. The first one is super intuitive. It's probably what you're already thinking. Get a bigger sample. Or, to go back to our soup, just use a bigger spoon. The larger your sample, the more likely it is to look like the real population. And you can really see the power of this here. Look, with a tiny sample of just 50 people, that potential for random error is pretty high. Your results could be way off. But jump up to 1,000 people?
Whoa, that potential for error just plummets. Your picture of the population gets way, way clearer. But here's the thing. It's not always just about getting more people. It's also about getting the right people. And that brings us to the second major strategy, being really clever and strategic in how you build your sample in the first place. So let's look at two of these smart methods. First up is stratified sampling. With this, you basically slice your population into important groups, or strata, say different age brackets. Then you take a random sample from inside each group. This guarantees you get a balanced view and hear from everyone. Then you have cluster sampling. This is different. Imagine you want to survey high school students across the state. Instead of picking a few kids from every single school, you might randomly pick 10 entire schools and then survey every single student in just those schools. It's way more efficient when your population is naturally grouped together like that.
So what does this all boil down to? The goal of sampling isn't to get a perfect, flawless, high-definition photo of the population. That's impossible. The goal is to get a reflection that is clear enough and sharp enough to let us make confident, reliable, and intelligent decisions. So I'll leave you with this thought. The next time you see a news headline with a big poll number, don't just look at the result. Pause for a second and ask yourself, I wonder how they got their sample. Because now you know, that's where the real story is.